Hello and welcome back to another video. Today we're going to be looking at Trigonometry 7 and applications of Calculus 2. So as always, topic 1 is our review. So what we established in the last video is that if we have two integers, n1 and n2, which we're going to represent by being in the class of integers, and they are not equal to each other, then the integral of 0 to 2 pi sine n1x sine n2x dx is equal to 0. Now, functions sine n1x and sine n2x behave as they are vectors. They are perpendicular vectors, to be exact. Now, some quick vector review. We have vector 1 with its subpoints v1, let's do v1, 1, so vector 1, number 1, vector 1, number 2, and vector 1, number 3. Carry this on with another example. If we had like vector 2, say, would be v2 1, v2 2, v2 3, like so. We also established that the vector norm it looks like this, and it is the square root of all the individual values squared and added together. So it'll be like that, pretty much. So if we had like 1, 2, and 3, it would be 1 plus 4 plus 9, which would mean that the vector norm would be the square root of 14. We've also established that if we multiply two vectors, it's equal to the vector norm of both vectors multiplied together times the cosine of theta, theta being the angle in between the two vectors. Moving on to topic 2, we're going to be looking at functions that are vectors. Or functions as vectors. So as we've already established, if we have a vector and say it's vector 2, 1, 3, and we draw a grid like so, we can section it out like something like this with each of our axes. Then we go to 2, then 1, go up to 3, and that is our vector from the center of the grid to where this point is. So this vector is actually moving towards us. Now, we can also establish vectors in a 2D sense. So if we have a 2D graph, and we have numbers 1, 2, and 3, or I should say positions 1, 2, and 3, we can label each of these numbers as a certain height, I guess, on each one, and that is another way to represent this vector. So these are both ways of representing this vector. Now, we could also simplify this down to like a formula. So say if we had vector A, and its values are 1, 4, and 9, we could say that f of n is equal to n squared. So for each value, say f of 1, it would be n1, f2 would be 4, f3 would be 9, so on. We can basically plot this in a sense. That's another way of saying for each of these values. So say we had vector b with values, say, 3, 5, and 7. We could write this as f of n equals 2n plus 1, where each f value of those would be equal to each individual one. So n is basically its position in the thing. So if it were, say, we could draw a graph off this. We were given this, f1 would be position 1, and 1 squared is 1. Position 2 would be f2, 2 squared is 4, 3 would be 9, and we kind of can see this take shape. Now, moving on to topic 3. Topic 3, we're going to be looking at the theory that integration can be thought of as a dot product. So if we take our vectors from before, we'll have vector A and vector B, each with their own things. So we'll have 1, 4, and 9, and 3, 5, and 7, and we'll just keep it the same. Now if we multiply these together, these vectors together, we can write this out as a dot product, the name for multiplying these together, and we'll have 1 times 3 plus 4 times 5 plus 9 times 7. And you'll see we're just multiplying them together by group. Now, since these are all their own respective positions, we can basically say that this is clumping position 1, position 2, and position 3, and multiplying it times the other one. So we're going to do F for vector A and G for vector B, and we'll get something kind of like this: F1, F2, F3 times G1, G2, G3. Now what we can do is we can rewrite this as a summation, where we'll have 3 k to 1, and it'll be F of k times G of k, which we can rewrite out as the integral of a to b, f of x, g of x, dx. So just ordinary integration is a dot product of itself. If we work backwards in the sense, it's basically the same. Now, topic 4, we're going to be looking at a small geometric insight to this topic. So I'm going to write this in. Geometric insight. Now, let's say if we have f of x equals the sine of x, we can draw the sine of x on a graph like this, a wave, and it just goes up and it just goes down, and it'll keep going like this forever. So we need to establish some values for it. So let's say if we were doing this for the integral of 0 to 2 pi sine of x dx, then we could say that this is 0, this is pi, and this is 2 pi. So you can set our boundaries for this. Now, we're going to explain why, in this sense, cosine of x is equal to 0. Because if we integrate, it'll be minus cosine of x, 0 to 2 pi, which would compute out to negative cosine of 2 pi minus cosine of 0, which is equal to negative 1 minus negative 1, which is equal to 0. And the reason this is equal to 0 is because this up here is the positive side and this down here is the negative side. And this is, in a sense, symmetrical. This area here is the same as this area down here. So basically, it's equal to 0 because these areas cancel each other out. I'm gonna get a new page here just so this is a little easier to draw. So if we increase the number of sine of x, so we'll have sine of x, 2 sine of x, 3 sine of x, and we try and draw this out, it looks something like this. So sine of x, I'm going to mark the halfway point, sine of x would, be the same sine of x we've already looked at, just goes up and down, it's the same thing. What 2 sine of x does is it keeps it the same length, it just makes the curve taller. So 2 sine of x would look something like this. It passes through the same point but increases the height of the curve. Now, well, it's also the same thing for 3x. It just goes up and down even more. But it's all still equal to 0. Now, let's look at a few other cases. Let's say we have 1/2 sine of x 0 sine of x, minus 1/2 sine of x, and minus sine of x. Now, 1/2 sine of x is just sine of x, but shrunk in half, basically. So we have a smaller line for that. 0 sine of x, since it would be 0 on either side, the value is already 0, it's just a straight line. It just goes like that. That should not be up there. But it's just a straight line. Now, once we go into the negatives, it's going to start on the other side. So negative half sine of x is going to mirror the sine of x and go on the opposite side like that. And again, negative sine of x just mirrors sine of x. It goes a little bigger like that. Now, what if we did it the other way, where instead of doing the sine of x, we just do the x? So we had, say, let's say sine of x, sine of 2x, and sine of 3x. Now what that would do, this drawing is going to get a bit weird. So the sine of x is just going to be the same thing. It just goes up and down. I'm going to use markers here just to make this a little easier to visualize. It's going to go up to the top, hit the halfway point, come back down, and end out. Make that little line a little longer. Now, 2x, it basically halves the distance between here and here, between the next wave. It halves it. So in a sense, this one's going to do is it's going to go up the same height, come back down at the halfway point, go down and hit the cross part, then go back up, go back down to hit the cross, come back up, and that is 2x. Now 3 of x splits it into thirds, basically. So if we divide this, each half of this, into thirds, and we draw out 3 of x, it'll look something like this. It'll go up, it'll go back down, go up, go back down, go up, back down, and back up. So they all look a little different. Each one gets a little more scrunched. So increasing the sine of x makes it bigger, increasing the x makes it more scrunched. So what do we do in a situation where we have, say, the integral of 0 to 2 pi sine of x times sine of 10x dx? Now, we know it equals 0 based off of our previous assumptions, but what would that wave look like? Well, if we draw out our graph, here's what's going to happen. We're going to do this thing called amplitude modulation. So what we're going to do first is we're going to draw out the sine of x. It's going to go up, halfway point, go back down, like that. And then what we're going to do is we're going to mirror it. We're going to go underneath, back up, down on top. So now we have this sort of like egg infinity symbol shape. And that is the sine of x. Now, that sine of x is going to have an effect on the sine 10 of x. So normally sine 10 of x would just be really wavy and it'd just go like up and down, like up, down, up, down, up, down, up, down. But since it's multiplied, it needs to fit inside of the sine of x. So instead of going all the way up to the top, it'll go to maybe here, and it'll keep waving at like a really small frequency. But its waves will be within the sine of x like so. And that is amplitude modulation, because normal sine 10 of x would just be up at the top. So the sine of x has an effect on it and scrunches it down at certain heights so it fits better. Bye, guys.